Oh, yeah. I saw that. Dude, I really want
Okay. So we're looking at this last application where we're looking at mixing fluids, and so the fundamental physics is modeled by the law of conservation of mass, which is like the rate of change of some pollutant or some salt in the tank is going to be how much is coming in minus how much is going out. And this is like in grams per second. So if you have like 5 grams per second of salt going in, and 2 grams per second of salt coming, then that means your net change in the amount of salt in the tank is 3 grams per second. But they usually don't give you the inflow rate in terms of grams per second. They usually give you the like sort of saying like, oh, we're pumping in water at a concentration of 1 grams per meter cubed at a rate of 5 cubic meters per second. And so to find the inflow rate of pollutant, you just take the flow of volume of water going in times the concentration of pollutant coming in. So if you're saying I'm pumping in 5 cubic meters per second of 0.1 grams per meters cubed concentration, that means that you're pumping in essentially 0.5 grams per second of pollutant. And then that's fine for the inflow. But the outflow is harder because you're putting in diluted water. The concentration inside this tank is like 10 times higher than the water that's being pumped in. This is assuming like you're mixing in, you're well mixed, and then you're letting water pump out on this end. But the concentration of the water that's pumping out is kind of unknown because you're pumping in diluted water in a tank that's like more concentrated, it's being mixed, and then you're pushing it out. And so we don't know. It's for sure going to be like some number between 0.1 and 1 grams. It's never going to be more concentrated than 1 grams per meter cube because you're pumping in diluted water, but it's not quite going to be like 0.1 grams, the concentration that goes out, because it's being mixed with the more concentrated water that's originally in the tank. So the best you can say is it's some unknown concentration C of T, which is going to be the function that models the concentration in this tank at some given time T. So the concentration of the pollutant flowing out will be equal to some C of T. But the problem does say that we're going to have the outflow valve pumping water at the same rate water is being pumped in. So at least we know that the flow of volume water going out is also 5 cubic meters per second, just like the inflow volume. And so that's 5 cubic meters per second plus times, sorry, this is not plus, this would be times the concentration, which is the unknown. We're not sure what that concentration is. And so that together, this is like saying 5 times C of T. So you can write this differential equation. This is like C of T. So C of T, some unknown concentration, C of T grams per meter cubed. Again, these units will work out because you can cancel this meters cubed. You can cancel these meters cubed, and you'll get the grams per second. Because you want to use like this law of conservation of matter kind of as sort of like the rate of change of Q, which is whatever, salt or pollutant in the tank, is going to equal the rate coming in minus the rate going out. And so let's write that equation. So if you use the pieces that we just had and just write that equation. So I'll just write it like this. I'll just say dq over dt is equal to dq in, I'll just write in there, dt, minus the dq out over time. And I'll use colors so that, this is the orange one, which is the inflow, and this is the outflow. And then for our problem, so this is the fundamental physical, this is the differential equation that represents the law of conservation of matter. So now we're just gonna put the things we found before. It's going to be like dq over dt is here. So for our problem, this will end up becoming dq over dt is equal to the orange, which is the rate of pollutant flowing in, we just found was 0.5. So this 0.5 just goes here. So that's the orange one minus the purple one is just 5 times C of T. Now, it's common for us to not, well, we don't like, we want to solve for Q. Q is like, well, we want to both solve for Q of T and C of T, but this has Q and C of T in the equation at the same time. So I would want to just have only one unknown, you know, not just like have two unknowns in here. But the C of T is like concentration. So concentration is like a mass over volume. So I'll just say that this C of T can be written as amount in mass, amount in grams. Q of T is the amount of salt in the tank divided by the volume of the tank. And in general, I mean, the amount of salt in the tank is probably changing as time goes on. The volume could also change as time goes on in general, but in this particular problem, the volume of the tank is not, the volume of the water in the tank is not changing with time because you're pumping in water at the same rate you're pumping out water. So this, for our problem now, here would just be Q of T over what's the volume. So this C of T is supposed to represent the concentration at some time inside this tank. And it'll be the same as saying the amount in mass divided by the volume. And the volume, the amount of salt is probably changing with time, but the volume of water in this tank is what the whole time? It's constant and equal to, it's considered 100, yeah, 100, because it's like saying that you're having a tank that's filled with 100 cubic meters of water and is pumped in at a rate of 5 cubic meters. The outflow valve also pumps it out at the same rate, so it's always going to be fixed to 100. So concentration, if you remember from chemistry, is like amount over volume. So that will allow us to write a differential equation in terms of one single unknown Q, rather than having C of T and Q of T both be unknowns. So the C of T really just means Q of T over 100 in our problem. So then you'll end up getting a differential equation that looks like, let's use black. That looks like essentially this whole thing is the same. But you'll have 5, so I'll write it this way. So it'd be 5 over 100 times Q of T. All right, it's just this 100 and this 5 being multiplied to this Q of T. And this will have, like, this will be the differential equation we want to solve. And we're solving for Q. And of course, 5 over 100 is just 1 over 20. So we'll just write that here. So that's the, now we just have the differential equation we want. It's dq over dt is equal to 0.5 minus, so I'll write it in standard form as well. Why don't I just shove this to the left-hand side? So it becomes plus 1 over 20 q is equal to, and then there's a 0.5. And we can notice that this is just a constant coefficient because this is a constant here. You have a constant forcing function. So you have, this is just a constant forcing. So it's a method of undetermined coefficients. This isn't hard to solve, so we'll just quickly do that right away. So we'll just say the particular solution is going to be QP is equal to some constant A. Plug this in. The constant's derivative of constant 0 plus 1 over 20 times the A is equal to 0.5. And so it's just going to be multiplied by 20 to both sides, but half of 20 is 10, so therefore your A is 10. And we found the particular solution. The homogeneous solution, you just read off. So basically your general solution would be Q of T is equal to this 10, plus the particular homogeneous solution is just reading off this is going to be C times e to the negative T over 20. So you got your, just use this color here and say this is purple because that's the particular solution. This is your homogeneous solution. And that's your general, this is your general solution. But you want to find what your solution would be. You want to plug in the initial condition. So you'll plug in the initial condition on Q, right? So this capital Q. So what is the initial amount of salt in the tank? They actually don't give it to you directly. It just says here that consider a tank filled with 100 cubic meters of water, and the water contains salt at a concentration of 1 grams per meter cubed. So it tells you the concentration. It also tells you the initial volume. But using that, you can, so remember that there's this, I'll just write it here and say, we know that C of T is equal to Q of T over V of T, right? That's just, from chemistry, concentration is equal to amount divided by Q is the amount. So Q is the amount divided by the volume. So if you wanted to know the initial Q, the initial amount of salt in the tank, you want to use this, but they give you concentration and volume. So that means that you'll have to say that your Q, initial Q, well, of course, if you solve for Q from this, you'll get that Q of T is equal to C of T times V of T. So it's not that surprising. If you think about, tell me the mass of salt in the tank, well, it would be the volume times the concentration. So if I said that there's like 1 grams per meter cubed concentration of salt, and there's 100 cubic meters of that, then you can tell how much salt must be in there by just saying 1 times 100. And so basically your Q naught is going to equal the 1 grams per meter cubed, which is the concentration, C of T, multiplied by, I have liquid at that concentration, and I have 100 cubic meters of it. And then obviously these meters will cancel, these meters cubed will cancel. And so your initial amount of salt in here is just 100 grams. So you're going to say Q naught is equal to 100. How would that, then what would that give you for the C? That means you're plugging this into the differential, no, not the differential, the solution. So you're going to say 100 is equal to 10 plus C times e to the 0, because you're just saying the initial time. So that means T is equal to 0, and 0 divided by 20 is 0. So you just get this, which is just 1, because e raised to 0 is 1. So C is equal to 90. And then you got your full solution with your initial condition as well. So you'll get, in the end, Q T is equal to 10 plus the 90 C negative T over 20. They also ask for the concentration of the salt in the tank, but we know that concentration is the same as Q of T divided by V of T. For our problem, it would be Q of T divided by 100, because that's the volume is fixed. So it's literally just take this and divide both terms by 100. So the first term will become 0.1, because you're just moving the decimal twice, plus 0.9 e to the negative t over 20. So this would be your concentration as a function of time. This will be in grams. This Q would be in grams. That's amount of salt as a function of time. And then this would be your concentration, and that would be the Q, which is measured in grams, divided by the 100, which was measured in cubic meters. And that's the concentration as a function of time. So if you took this red expression, which is the concentration, and you ended up plotting it, you will get this red graph. This is plotting the concentration of the salt in the tank as a function of time. It definitely has the correct initial condition because it says the water contains salt at the concentration of 1 grams per meter cubed. So you see the 0.01, so time 0, it is 1. And it's going to exponentially decay because you have this e to the negative t over 20. So as time goes on, this is an exponential decay. In the infinite time limit, you're going to essentially get that this second term goes to 0, right? Because you're going to have e raised to the negative infinity, and that disappears, which means that as you keep going forever forward in time, it's going to asymptote to a concentration of 0.1, but never go below that. And why would it never go below 0.1? Yeah.
So that's the concentration was flowing in, so it's completely replaced.
Yes, exactly. Yeah, we're pumping in diluted water. That's 1/10 of the original concentration in the tank. And after a while, it's just going to completely recycle it, replace it, kind of, because it's a well-mixed tank. And you're just pumping in diluted water, pumping water at the same rate out, and it's just going to completely replace the water inside to a concentration no lower than 0.1, because you're not pumping in pure water. You're pumping in some salt water, but it's very diluted salt water. So it's gonna ask to never go below that over time. So solving this differential equation is just method of undetermined coefficients with constant forcing. And that's not bad, but it's probably the setting up the equation that might be a little challenging with these kinds of problems. But it's really this green box. The rate of change of some species could be salt or pollutant or dye or some chemical in the tank. The rate of change of it will equal the rate of change, the rate coming in and the rate going out, so you can't create or destroy matter. And so that's the physics, but then you got to interpret what each of, like, say, this orange term, the inflow rate and the outflow rate, you have to interpret what those are. And the inflow for this one was just fixed. Just pumping in some rate at some concentration the whole time. But the outflow is a little harder because the actual concentration that's going out is actually your unknown. You don't know how much is that concentration. That's why I left it as C of t, which is equal to Q of t over V of t, and Q of t is one of the things we want to find. Okay, so let's look at this one is like a continuation of the other one. Okay, so with water flowing out of the tank through an outflow valve at the same rate as it is being pumped in, find the rate the less salty water should be pumped into the tank so that the salt concentration becomes half in 10 minutes. Okay, so let's just build the same. So this one's a little bit weird because it's saying find the rate that you want to pump less salty into the water so that the salt concentration becomes half in 10 minutes. We're going to use the same fundamental equation, this one right here. But some stuff is going to change. So we'll just say, okay, let's figure out what the equation would become. dq over dt is equal to dq that's going in. So the inflow rate is going to be, what did we used to have? We had like 5 cubic meters per second being pumped in at a concentration of 0.1 grams per meter cubed. This one's saying okay, we're still flowing water out with pumping in, and it's the same water, the rate of flow out and in are the same. Find the rate the less salty water should be pumped into the tank, so the salt concentration becomes half in 10 minutes. What we are going to say here is, let's say water flowing in and out at the same rate it's being pumped in. So we'll just say like the water that's, let's just maybe use this picture again. So I'll just copy and paste this. Well, I'll just draw it. So let's draw the picture. So you have a tank. You've got inflow, outflow. Okay, so water going in is going to go in at a rate of some cubic meters per second, but we're not sure what that is. So we'll just say it's like R is the rate, cubic meters per second. Okay. And let's have the same concentration is 0.1 grams per meter cubed. So everything is still the same, 0.1 grams per meter cubed. So find the rate, the less salty water. So this less salty water is still the 0.1 grams per meter cubed. And so that's grams per meter cubed. But we don't know what rate we want to pump it in. But whatever rate we're pumping it in, we're assuming that we also pump out the same rate, R cubic meters per second. But the water that's pumping out, we still don't know what the concentration of that is. So it's going to be whatever diluted water goes in, it's going to get mixed, and then it's going to come out, and it will be, probably something. So it's still the same. So this rest of this is still the same. So right here is the concentration initially in the tank is 1 grams per meters cubed, and then the amount of salt in there would be like 100 grams initially. So this is all the same. The only thing we're changing here is that assuming the water flowing out of the tank as is going out at the same rate that's being pumped in, find what that rate must be so that when this less salty water is pumped into the tank, we can make it so that the salt concentration in the tank becomes half in 10 minutes, which means that we want the initial concentration is 1 gram. So we're trying to get it to be like half a gram after 10 minutes. So let's just bring this down. So we have this is our differential equation will look like this. So dq over dt is the flow in. The flow in is 0.1 grams of concentration multiplied by a rate of R minus your outflow is going to equal your amount of your concentration, which is going to be C of T, but C of T is just equal to Q of T over 100 again, because we're pumping in at the same rate. So this will be Q over 100 times the R, which is the rate that's going out. Both of them are the same rate going in and out. It's just that you're pumping in a concentration of 0.1, and the water that's being pumped out is whatever concentration you have at that time, divided by or whatever amount of salt you have at the time, divided by 100. So this is our equation. So we're leaving R to be some rate that we're going to try to find later, but we know that the rate going in and going out are the same. So we're leaving that R. It's going to be some number eventually, but we're going to find that number later. And so this is our differential equation that you can write in standard form by shoving all the Q terms on one side. So you'll have dq over dt. You add this, so it'll be like, I'm just gonna write it this way so that it's clear that the Q is, I'll just write Q is the unknown, and then you have 0.1 times R. And R is a constant, so I'll just say R is a constant. It's the inflow / outflow rate. And that means that this is also a constant input. So or constant forcing. So your Q of P will equal A, some constant A, and you're going to plug this in. you take the derivative of a 0 plus r over 100 times a is equal to 0.1 r. And you're just going to multiply by 100, which is going to make the 0.1 become a 10, but you're dividing by r, so you get a is equal to 10. It's kind of the same thing we had before. So we got our particular solution. Now we know the general solution. Q of t is equal to the 10 plus this right here. It's going to be c e to the negative r over 100 times t. So this is just the particular solution plus the homogeneous solution. This is supposed to be purple. And this is the homogeneous solution. Okay, and we still have the same initial condition. So we're saying that at the start, the tank has 100 grams of salt. So you can plug that in and get 100 is equal to 10 plus c times e to the 0 again, because you're just plugging in 0 for t. So c still is 90 again. And so our full solution for this will also be very similar to before, but just has that r. It's going to be 90 times e to the negative r over 100 times t. And this is like the amount as a function of time of salt in the tank. Of course, if you want the concentration, then you just take it and divide it by the 100. So of course, this is the Q of t divided by the volume 100. So you'll get the same thing we had essentially before, which is 0.1 times 0.9 times e to the negative r. Let's move this down. Negative r over 100 times t. That'll be the concentration as a function of time. And we kept this r just kind of general because we're just saying, okay, we're trying to figure out what's the rate that I want to pump water in, and we're assuming that we're also going to pump that same rate out, so that the concentration becomes half in 10 minutes. So that means that now that we left the r as some general rate that we don't know, we're going to assume that we're going to keep the pumping rate constant. That we want to find that constant pumping rate so that we can make sure that the salt concentration in the tank becomes half of the original. So that means, what does that mean? So I'll just write the condition that we want at that point. So this just says that we want this to be half. So I'll just say, so the salt concentration becomes half in 10 minutes. That means that you want C at 10 to equal 0.5. Because your initial C is this. So this is what we want to have. So that's another condition that you're going to plug into here to find this R. So you're going to say 0.5 is the concentration we want. 0.1 plus 0.9 times e to the negative r over 100 times at a time of t equals 10. T equals 10. So that's the, I'll just move it here. So this condition that we want the concentration in the tank after 10 minutes to become 0.5 is like saying, take the concentration. We want to find the R that would make that happen. So this is just salt algebra at this point. So it's just going to be, I just,
Zero.
so the initial concentration in the tank is 1 gram. This 0.1 is there just because it's like saying in the infinite limit, it's going to take the exponential decay, will go away, and you'll have a concentration in this tank that's going to equal the diluted. Yes. Or what happened? Oh, did I change up the... Oh, okay, so I guess this one was in seconds up here, and then I suddenly said minutes here.
Yeah, you use 600.
Did I use 600? Oh, yeah, that's probably what I want to do then. So what is 10 minutes? 10 minutes is 600 seconds because it's 60 times. So let's do that. Yeah, 600. So that means I really want this to be C of 600 is equal to 0.5. Yeah. So we want at 600 seconds. Yeah, so that means it's 600. It's good. Because the graph also does that, yeah. So 600 seconds, we want it to become 0.5. So we just solve this. We subtract by 0.1. So you get 0.4 is equal to 0.9. E to the 600 divided by 100 is just 6. So it's going to be negative 6R. You can divide both sides by 0.9, which is going to be like the same as 4 over 9, because 0.4 over 0.9 is going to be the same as 4 over 9, is e to the negative 6R. And then you take the ln, so you'll just say ln of 4 over 9 is equal to negative 6R. So your R is going to equal negative ln of 3 over 4, or 4 over 9, divided by the 6, okay? That is just going to be some decimal. You get like 0.135 meters cubed per second is the rate that you'd want for the tank to be. I don't know if it's hard to read, so I'll just make it black. So it may be easier if I just made it black. So that's the rate you want to be pumping water in. And then we're assuming also that same rate is going to be pumped out as well. So, you know, like the question is like, we know that if I pump water, this one was saying I'm pumping in water that's diluted at a rate of 5 cubic meters per second. We for sure know that as time goes on, the concentration in the tank will go down. But let's say you're some engineer and your boss is saying, I want you to figure out the flow rate that I want you to pump into the tank to make the salt concentration in the tank equal 0.5 grams per meter cubed at exactly 10 minutes from when you start pumping it in. Because then it's obviously like you pump, this first one was just pumping in at 5 cubic meters per second. So you know it's gonna, you know, get less concentrated with time, but you can tune that, right? You can be like, I'm pumping in this diluted water faster or slower, then you can get the tank to actually have less concentration faster or slower. If you pump in pure water, it's gonna actually dilute faster. So you know, that's something you might want to tune, or you know, and so you might make that it kind of an unknown. You'll say, well, I don't know what the inflow and rate will be. Let's just call it R. And then I build a whole, well, differential equation with R left in it, and then solve it. Your solution will contain R in it. And so it's like saying this is the evolution of the amount of salt in the tank as a function, and then you just take that and divide it by the volume to get the evolution of the concentration in the tank, the salt in the tank with time, with R still in there. And then it's very intuitive. This R, the higher this R is, the faster this exponential decay term goes away. And the faster you'll reach the asymptotic 0.1 grams per meter cubed. So the slower the R is, then the exponential decay term would decay slower. And so this is just saying, tell me what that R has to be so that the concentration in the tank will be 0.5 grams per meter cubed at exactly 10 minutes from the moment I pump it in. Okay, so that's, you know, I don't know, maybe there's some application for that, but that's, you know, a problem that will leave these rates unknown until the end, and you fit this concentration to, you force it to have this concentration at some given time, desired time. But the equation is still the same. It's this, like, you know, the flow, the change in amount of something in the tank is the amount coming in minus the rate coming in and the rate coming out. So that's still the same. So for both of these problems, we had the volume fixed. So it was like the rate that's going in is the same as the rate going out. So the net change in volume of liquid in the tank remained the same, like 100 cubic meters the whole time. But you may have a situation where you're pumping in water at a faster rate than you're pumping out. Of course, your tank will have to be bigger. because you're just gonna have like more, it's gonna have more liquid filling in. So assume like this tank is actually like this tank is actually like bigger and it can hold more liquid. So you're like pumping in more water. Of course, there's going to be a limit because if assuming this tank is not infinitely large, there's going to be a limit where it's going to maybe just overflow from the top or something like that. But let's say there's like a tank that's like pretty big, and then you're just pumping in water that's fast at a faster rate. So let's say that you have some tank. Let's say this tank is like a big tank. It's filled with 100 cubic meters of water, again, containing a salt concentration of 1 grams per meter cube. But now the diluted water, the less salty water, with a tenth of the concentration, is being pumped in at a faster rate of 10 cubic meters per second. So remember, before it was 5 cubic meters per second, but now we're pumping in water at 10 cubic meters per second. But the water flowing out of the tank is still kept at 5 cubic meters per second. So like before, this is going to still stay as 5 cubic meters. So you know that you're going to have more water accumulating in this tank with time. The concentration of the water going in is still the diluted 0.1 grams per meter cubed. The water going out is again still unknown, some concentration C of T grams per meter cubed, because it's going to be whatever ends up being the mixed version of the diluted and the tank and whatever liquid that's in here. So determine the actual like concentration as a function of time, the amount of salt as a concentration of time for this situation. It's still going to be the same equation as this one up here. So I'll just copy and paste that and bring it down again. It's still going to be this, but our terms are going to look a little different. So we're going to have dq over dt is equal to, the inflow is still going to be the same as just these multiplied together. So I guess I'll just write it separately up here and say, what is our dq in over dt? It's going to be your flow times the concentration. This is like this right here, these two little expressions here. So to get the dq in over dt, which is the grams per meters, or grams per second, you'll have to do the flow rate, which is 10 meters cubed per second, times the concentration, which is 0.1 grams per meter cubed. Of course, the meters cubed cancel. So you get the thing we got before, which is like 1. Well, no, this won't be what we got before, because before it was not 10, but 5, but this will just become 1 grams per second. So if you're pumping in 10 cubic meters per second at a concentration of 0.1 grams per meter cubed, then you're pumping in 1 grams per second of salt. Now the dq out over dt will also be like flow times the concentration. And the flow going out is still going to be the 5 cubic meters per second, which is half the rate that's coming in, times some unknown concentration, C of T, which is going to be also grams per meter cubed. And this will actually work out. But the issue is like, what is our C of T? So I'll just write this as, this is the same as 5 times C of T is the same as Q of T over V of T, right? And for sure, the Q of T we don't know because that's what we're trying to solve for. But the volume here used to be 100, right, before. But this volume is not staying fixed to 100 anymore. What is the volume as a function of time? It's initially got 100 cubic meters. You're pumping in 10 but pumping out 5. So the volume, which I'll use blue for, so this expression in the denominator here can actually be written as a function of time. If I told you that the initial volume in the tank is 100 grams of or meter cubed of water, and I'm pumping in 10, pumping out 5, what's your net gain of volume per second? 5. So can you come up with an expression that would model volume as a function of time? Yes, good job. So that's different from before. 100 plus 5t is actually the amount of change in the volume that's going on in there. And so that's now going to be your flow out. So what do we have? We have your inflow rate is 1, and then you have is going to be whatever goes in minus whatever goes out, and whatever goes out is going to be this right here. 5 times Q of t over 100 plus 5t. Okay, so this is our differential equation, but let's write it in standard form. So we'll write it in standard form, means that I will just say it's going to be dq over dt. Move this over, so it's going to become 5 over 100 plus 5t times q is equal to the 1 on the right-hand side. The 5 over 100 plus 5t, so you could just factor out a 5 on the bottom and then cancel with the 5 on the top. So this will end up being the same as dq over dt plus 1 over 20, because after you pull out a 5, plus t times q is equal to 1. So this is like the simplified version. So there's something really different about this equation than what we had before. A question how do we solve this type of equation? Differential equation. Can we use the method of undetermined coefficients? And why not if we can't use the method? This is not a constant. And that wasn't a problem before because our v of t was 100 before, and that's the reason this is not a constant in front of this q is because we ended up dividing by not just 100, but this 100 plus 5t. This is not constant, so you have to use what method? Yes. Yes, you have to use the there's no other method that you can use but the integrating factor, because this also is not separable. So you have to use the integrating factor in order to solve this one. And so let's do that. Let's say what the u is going to be. The u is going to be e to the integral of p of t dt, where our p of t is equal to this 1 over 20t. So it's going to be the integral of our p of t is going to be this. So it's going to be dt over 20 over plus t. And you can just take the integral of that. So you'll just get that this is the same as dE of ln of 20 plus t. And then you can just cancel the ln and the 20 and the e, and then you'll get this is 20 plus t. It's the integrating factor. So what do? We multiply the whole equation by this integrating factor. So you're just going to say, I'm going to multiply this whole equation by u, which is like going to give us, so by design, if we computed the integrating factor correctly, the right-hand side becomes dt times the u, which is the 20t plus, or 20 plus t, times the q, right? Equals the right-hand side will become just 1 times u, but the u is just 20 plus t. This is like the integrating factor. Then you take the integral of both sides. And so this right here, right, the inside of this is always going to be u times q. I mean, in the past, our variable was x, so it was always like u times x, but in our problem now, it's going to be u times q. And then the power of the integrating factor is that the derivative and the integral will cancel each other. So you're left with 20 plus t times q is equal to the integral of this, which is going to be 20t plus t squared over 2 plus some integration constant c. And then you can just take this and divide everything by the 20 plus t. So you get, therefore, your q of t is equal to, I'll just write this in the order t squared over 2 plus 20t plus c, all divided by the 20 or t plus 20. This is the q, so this is just saying like what's the rate, what's the amount as a function of time in grams. But if you wanted to also find the constant concentration, then you just divide this by the volume. But the volume is actually this. So I'll just say this is Q of t divided by the volume is 100 plus 5t. So you'll end up getting the t squared over 2 plus 20t on the plus c on the top will still stay the same. But you'll have this is divided by another factor of this being multiplied with this. So you can factor out a 5 and then just end up having t plus 20 squared. That's just algebra. And this will be the concentration as a function of time in grams per meter cubed. So this is like the evolution of the concentration and the amount of salt. The C you would have to find by plugging in the initial condition. So I'll probably show the work for that, but the initial condition for the Q is going to be how much salt do you have in the tank at the beginning is 100. That's still the same from before. So this is this stuff right here. So Q0 is equal to 100. If you plug Q equal to 100 in here, you'll get C is equal to, it turns out that it's equal to 2000. Because you just plug in 0 for all the T's, 0 for this. So it's going to be 100 times the 20, and it'd be 2000. And this plot right here is plotting the amount of salt as a function of time. It's actually growing for, it's initially the sum amount is 100 grams initially. You're pumping in diluted water at a faster rate than you're pumping out, so it's going to dilute. But then after a while, it's just getting more and more amount of salt. And the reason behind that is because you're just pumping in more water with diluted salt in it, but there's just more water in the tank at that point. So it's going to be like, instead of 100 cubic meters, it'd be 200 cubic meters. Even if it's diluted, the actual amount of salt is increasing in the tank because you're pumping in more and more water and it's just accumulating. So the concentration is definitely getting lower. So if you plotted the concentration, it'll look like kind of like this. And it'll just plateau. But the actual amount is actually, well, I'll talk about this a little bit more, but the punchline is variable volume, you have to use the integrating factor because you don't have a constant coefficient. And I think I have office hours right now, but we'll go next door.
Thank you.
Thanks.
It's